Hello everyone. Today we're going to talk about continuity. In the past, we always said continuity was simple. Can you draw your graph without picking up your pencil? Today we're going to give a more mathematical definition of continuity. And that is, a function is continuous if the function is defined. In other words, it exists. There's a point there. So is there a point there? The limit exists. That means the left limit equals the right limit. Both sides are going to the same place. The left and right side are going to the same place. And if the point equals the limit. So, when is something continuous? When the point exists, when the limit exists, and they're both the same thing. There's two types of discontinuities. Two types of things that make a function not continuous. One is called removable, and that happens basically when you can factor and cancel. If you can factor and cancel, that means that you've removed the discontinuity. Non-removable means that there's no way to get rid of that. So like jumps, infinites, and oscillating, and I'll show you here what those mean. Removable discontinuities are a hole, just a simple hole in the graph. Because if I wanted to, I could take one point and fill in the hole. However, this graph I can't fix. If I put a point here, then it's not a function anymore. It fails the vertical line test. These types of discontinuities happen at piecewise functions. Infinite asymptotes. What causes an infinite or an asymptote? It's when you divide by 0. If you end up dividing by 0, you're going to create an asymptote or a hole. The hole you can cancel out through factoring, the asymptote you can't. And the third is oscillating, which is so rare we're not going to talk about it for right now. Let's take a look at a removable discontinuity. This problem right here, if you plug in 1, so if you do 1 minus 1, or 1 minus 1, you get 0 over 0. Which means I can factor. The top is x minus 1, x squared plus x plus 1. Bottom is x plus 1, x minus 1. These will cancel, and now I just plug the 1 in here and here. And I get 3 halves. So if I were to put the point 1 comma 3 halves into that graph, then I would fix the hole. I would remove the discontinuity. And that's why that type of discontinuity is called removable. Okay? As a summary, a function is continuous if the left limit equals the right limit, which equals the regular limit, which equals the point. They're both going to the same place, and there's a point where they meet. In other words, the limit exists, it's the same as the point, and the function is continuous. You see removable discontinuities, which are holes, and then non-removable discontinuities, which are jumps, infinite asymptotes, and oscillating. Let's try a problem. It wants to ask about if x equals -1. Is it continuous? No, since the limit as x approaches -1 does not exist. The limit doesn't exist there because the function doesn't go to the same place. The left side goes to the hole, the right side goes to the dot. What type of discontinuity is it? It is a non-removable jump. And then where is it continuous? People have trouble with this question. It's continuous everywhere, except at -1. So it's continuous every place else in the graph, except for that one jump discontinuity. Is it continuous at 3? No. Since the limit, as x approaches 3, does not exist. Also, f of 3 does not exist. So this one's not continuous for 2 reasons. The limit doesn't exist because one side's going up forever and one side's going down forever. And the point doesn't exist because there's an asymptote. What type of discontinuity is that? Well, it's non-removable. It's a non-removable infinite discontinuity. Infinite. Where is it continuous? Well, it's continuous everywhere except that discontinuity we just talked about. There's another discontinuity right there, which is x equals 0. It didn't ask, but I'm going to answer the question anyways. This is a removable discontinuity, which means it's a hole. Last example. Piecewise functions. Ask yourself, is that graph continuous between 0 and 3? Yeah. This graph, if you plug in 0, you get 1. If you plug in 3, you get 4. And it's continuous between those 2 points. You can take the square root of any number you want to between 0 and 4. Is this graph continuous? Yes, that's just a line. That line goes through y equals 5 and has a slope of -1. So it's continuous from 0 to 3, and it's continuous from 3 to 5. If it was going to be discontinuous, at what point would it be discontinuous? Where it hooks together. So I'm going to plug in the point 3 into both of these equations. I'm going to plug it into the left side. And if you do that, you get 4, square root of 4 is 2. And the right side. If you plug it into the right side, you get 5 minus 3, which is 2. And that tells you, because those two things have the same value, that the limit as x approaches 3 from both sides of f of x equals 2. But that's only one half of the proof. The other half of the proof says, does the point exist? Well, 3 is right there, so I'm going to plug it in right there and say that f of 3 equals 2. The point exists and the limit exists, and they're the same. So what's that mean? It means it's continuous. Remember, to be continuous, the limit has to exist, the point has to exist, and they have to be the same.